So a lot of times when you're drawing a Lewis electron dot diagram, like we saw in the previous video talking about resonance structures, is there's many different ways to draw molecules that still obey the octet rule. Okay, there are times though, especially on the AP test, where they will draw different molecules for you. They'll do the whole thing, and then they'll ask you which of the structures is the most reasonable. Okay, and one of them might obey the octet rule, one of them might not. Okay. If they mention this term that we're discussing here, that's called formal charge, if they mention formal charge, then you do not consider the octet rule at all. Okay, and that's a real important part about formal charge is when they say which of these structures is the most reasonable or what's the best representation of this molecule, and then they say justify your answer in terms of formal charge. That means you forget about the octet rule altogether and you only focus on what's called the formal charge. Okay, and that's actually one of the nice things about formal charge is you never ever think about it unless they specifically mention it, unless they say, justify your answer in terms of formal charge, or they use those words, formal charge, in some way or another, then you never even have to consider it. You always just draw the Lewis electron dot diagram based on the octet rule, where you're trying to get everything to have 8 electrons. Okay, and so first of all, so let's back up here a little bit. So formal charge you never ever even consider unless they specifically mention formal charge. Okay, so don't ever talk about formal charge unless they do. And if they do say justify your answer in terms of formal charge, again, completely forget about the octet rule altogether. So what is formal charge? Formal charge is obviously a charge. It's the charge that an atom would have if all of the atoms had the same electronegativity, which means if those electrons were shared equally between both atoms, it's the charge that an atom would have. And the structure with 0 or the lowest formal charges is the most likely or the most reasonable, is the best representation, however you want to say it. Okay. So when you're determining the formal charge on an atom, number one, you start by looking at the atom in question and then looking at the number of valence electrons that atom has. So let's look at something really, really simple here that will help us hopefully to understand this. Okay, so here's the CO2 molecule. So you have to have a Lewis electron dot diagram to do this. Okay, so number one here says use the number of valence electrons around the atom in question. So let's say they're asking about the formal charge of carbon. Okay, well, we could do oxygen as well. Okay, how many valence electrons does a carbon atom have? I look at the periodic table. I see that carbon is in the 4th row. So it has 4 valence electrons. I look at oxygen. Oxygen is in the 6th row, or in the 6th column. So it has 6 valence electrons. Okay, then number 2 says subtract the number of non-bonding electrons around that atom in the Lewis structure. So right here, there's 2 non-bonding electrons, and there's 2 more. So we're going to subtract 4. How many non-bonding electrons does carbon have? 0. Okay. So that's what we've got so far. And then number 3, subtract the number of bonds also around that atom or atoms. Okay, and only count each bond as 1 electron. Remember, we're pretending like both atoms have the same electronegativity, so those electrons in the bonds are shared equally. So each bond, for example, right here, we're basically going to cut these bonds in half. So 2 electrons go with the oxygen on the left, and then 2 of them go with the carbon on the right. So you subtract the number of bonds from, again, that number. So how many bonds does carbon have? How many electrons does carbon have surrounding it? 1, 2, 3, 4. Again, just count each line as 1. So 4 minus 4 is 0. Okay, in terms of oxygen, how many bonds does it have around it? Okay, 1, 2. Okay, so in this case, carbon and oxygen, and this oxygen here as well, because it's the same as the oxygen on the right, they all have formal charges of 0. Okay, if you were to draw carbon dioxide with a triple bond here and a single bond here, notice what that does. Oops, that's too many electrons. So 2 dots on this one and 6 on this one. Okay, this carbon still is going to be 4 minus 4, still 0. Okay, this oxygen, though, is going to be 6 valence electrons. And watch, I'm going to do it a little bit quicker this time. Okay, 1, 2, and then 3, 4, 5. 6 minus 5 is positive 1. So what we do is up here in the corner, we put a little positive, and that means that that oxygen has a formal charge of positive 1. The oxygen over here on the left, again, 6 valence electrons minus 2, 4, 6, and then the bond makes 7. So 6 minus 7, negative 1. Okay, so that's one of the reasons why carbon dioxide has the 2 double bonds and not a triple and a single, is because the double bonds produce a molecule that have no formal charges on the atoms. Okay, and that's how you would explain that. Why is CO2 best represented this way is because there's no formal charges on the atoms. Okay, now do note as well, what's kind of cool about the formal charges is CO2 does not have a charge on it. Okay, it's just CO2, nothing up in the corner. Okay, but notice you got a minus 1 and a plus 1. They do basically cancel each other out. The sum of the charges will always add up to the charge on the molecule. So like in, let me show you another one, like in CO3 2 minus. Okay, the formal charges are going to add up to negative 2. Okay, so let's go ahead and draw that. Remember, CO3 2 minus has resonance structures. We saw that yesterday in the previous video. Okay, so this carbon right here, again, I'm going to do this quickly. 4 minus 4, 0. This oxygen up here, 6 valence electrons, minus 4 for the electrons, minus 2 for the bonds, 0. But this oxygen down here, 6 valence electrons, minus the 6 dots, minus the 1 bond is negative 1. This oxygen's negative 1, and this oxygen, it's the same as the other one, is also negative 1. Notice that there are 2 negative 1 formal charges, and so that produces a charge of negative 2. Hey, what a surprise. The charge is negative 2. Okay, the other note. If you can draw a Lewis electron dot diagram that uses all of the valence electrons and obeys the octet rule, you don't try to, wait, I drew it, but it has formal charges, so I don't know what to do. Okay, you don't draw a better molecule with lower formal charges, again, unless they specifically ask you about formal charges. Don't ever consider it unless they use those exact words. Okay, now in general, okay, the better representation is the one that has fewer formal charges on it. Okay, so usually with formal charge, the way that you're going to determine which one's better is by which one has fewer or no formal charges on the atoms. Okay, if they both happen to have, and yes, this has come up on the AP test, if both molecules do have the same formal charges, though, let's say there's a plus 1, minus 1, and then there's a plus 1, minus 1 on different things. Okay, well, wait, which one's better? There's a plus 1 and a minus 1 on both. Okay, then the only thing that matters then is the Lewis electron dot diagram in which any negative charges reside on the more electronegative atom. Okay, that is the better representation of the molecule. Okay, so here's an example of this. Okay, Lewis, and in your homework there's actually one as well. The one that deals with, I think it's HCNO. It's in your homework packet. That is one that is this idea of the more electronegative one is the more important one. Okay, so 2 Lewis electron dot diagrams can be drawn for the OPF3 molecule as shown below. Which of the two best represents a molecule of OPF3? Justify your answer in terms of formal charge. So if you say structure 2 because it obeys the octet rule and everything has 8 electrons, you are wrong. Okay? Normally, if I were to tell you draw OPF3 and draw it with P in the middle and put everything else around it, of course this is exactly how I would expect you to draw it. But when they say justify your answer in terms of formal charge, it means forget the octet rule altogether and only focus on which one has fewer formal charges on it. Okay? So, again, I'm going to move a little bit quickly. The phosphorus has a +1 formal charge on this one. The oxygen has a -1 formal charge. Okay? Hopefully you can see that. All of the fluorines are 0. Okay? On this structure over here, there's nothing to draw because there are no formal charges. The phosphorus is 0, the oxygen's 0, and the fluorines are still all 0. Okay? So which of the two best represents a structure of OPF3? Absolutely structure 1. Okay? And how would you justify that? Because none of the atoms in structure 1 have formal charges. And in structure 2, there are formal charges. Okay, hopefully you're listening to me since you probably can't read that. Somebody told me once, Mr. Johnson, you should be a doctor. Okay, because your handwriting's so bad, no one can read what you're writing, which is probably true. Okay, example 2. 3 compounds that contain an element from group 18. So again, group 18 start at hydrogen and go all the way across. Group 18, again, are the noble gases. Okay, so you've got a bunch of them here. Possible Lewis electron dot diagrams for the compounds are shown below. Which structure, A, B, or C, which means for this question, forget about D and E, okay? we're not worried about those. Which structure, A, B, or C, minimizes the formal charges for each atom in that XeO2 F2 molecule? Justify your choice, okay? So again, I'm trying to find one that minimizes the formal charges. Okay, so I'm just kind of looking at A, and I'm kind of focusing on xenon and oxygen, because the fluorines, all of the fluorines I can see have the 6 dots plus the 1 lines. That's 7, 7, 7, 7, 7. All the fluorines are fine. Okay, none of the fluorines have formal charges. Okay, but I do see that this oxygen with a single bond is -1, -1, and the xenon, remember, has 8 valence electrons. So minus the 4 bonds and then minus the 2 dots is +2. So that xenon is +2. Notice again that the minuses and the minuses cancel out with the +2, but they still have formal charges. So that one's probably not it. Okay, let's look at this one here. This oxygen on the bottom is -1. The xenon is, again, 8 minus the bonds, the bonds, 1, 2, 3, 4, 5, minus the 2 dots is +1. So we've still got this one. This one is better than this one because it does have fewer formal charges. But now let's keep going here, okay? The oxygens with the double bonds are both 0, and then xenon, again, is 8 minus the bonds, 1, 2, 3, 4, 5, 6, and then minus the 2 dots, 0. So what is the best representation? Absolutely structure C. So which structure? Structure C, and justify your choice because, again, none of the atoms have any formal charges. Okay, and on question, it was question number, let me make sure, yes, it's question number 70 in your homework packet that has the HCNO. It is drawn for you, but like this example here, example number 2, they are drawn for you, so all you have to do is go through it, just like we just did here, and identify the formal charges, and you're going to find that they're going to be the same. They should be the same unless you made a mistake. So in that case, then you have to look, okay, where's that negative charge? Is the negative charge on wherever the 2 negatives are, whichever one has the negative on the more electronegative atom, that is the better representation. So looking at the periodic table, oxygen, of these 4 elements, oxygen is the most electronegative. It's the closest to fluorine. So if the negative charge is on the oxygen atom, if that formal charge that's negative is on oxygen, then oxygen, then that's the better representation. Okay? If the negative charge is on like carbon on one and nitrogen on the other, then again, which one's more electronegative, carbon or nitrogen? Well, nitrogen, again, closer to fluorine, more electronegative. So whichever one has that negative charge on it that's more electronegative, that's the better representation. Again, that's only happened one time on the AP test, and I want you to see that question as well. This is from a very, very recent exam. So that's a more typical type question that you're going to see on the AP test.